Hello, and today we're going to do a quick thermal physics recap for paper 2 for A level. So let's start straight away. So let's start with the distribution of particles, n number of particles, and with particle speed v. And when you have in a substance and you have different particles with different speeds, you have a distribution like this and something like this. Let's draw two distributions. Wait, this is a bit bad. Something like this maybe. And then so these distributions they relate to the different temperatures. So this one, because it has a lower velocity of particles, there's a lower temperature, and this one's a higher temperature. So this one could correspond to 200 Kelvin, and then this one could correspond to 500 Kelvin. Now let's go on to the internal energy formula. So EI, which is the total internal energy, is equal to the kinetic energy plus the potential energy of the particles, of all the particles together. Let's go on to work done. So say you have a system with particles like this, moving about like this. To do work done, you can, to do work to the system, you can do work by heating into the system, and you can do work by cooling, by taking away energy from the system. And yeah, that's pretty much it. Let's draw a temperature diagram so we get phase changes, right? So to show phase changes, so we have temperature and we have EI, which is the internal energy. So at the start, when you start heating something up, the temperature increases and the internal energy also increases. But at one point, when there's a phase change, the temperature stays the same and the internal energy increases, and then to a point where it starts to carry on. So here there's a phase change, and the this is because the kinetic energy stays the same, because temperature is is related to the average kinetic energy, average KE, and then so the KE doesn't change, so K equals constant, EK equals constant, but the potential energy increases, so EP increases. Now let's go on to specific heat capacity equation. So delta E is equal to MC delta theta, where delta E is the change in energy, M is the mass of the substance, C is the specific heat of the substance, and delta theta is the change in temperature, and this relates to the change in energy. Let's go on to specific latent heat. So again, change in energy in a phase change is related to ML, where L is the specific latent heat. And you can get specific latent heat of two types. One is for fusion, and one is for vaporization. Yeah, so fusion is between solids and liquids, and vaporization is between liquids and gases. Let's go on to the conversion between Kelvin and degrees Celsius. So for Kelvin to Celsius, so Kelvin is C and Celsius, Kelvin is K and C is Celsius. We just add 273 to the Celsius to get the Kelvin scale. Now let's go on to the gas laws. So the three gas laws. The first gas law will have Boyle's law. So Boyle's law. And this is P1 V1 is equal to P2 V2, which is equal to a constant. And if we draw it on a graph of P and V, PV graph, we would get something like this. And this is when temperature is constant. Temperature is equal to a constant. The more temperature you have, the further the curve is away from the origin. So if you go out here, temperature increases. So each graph corresponds to a constant temperature, but largest temperatures are further away from the origin. Now let's go on to Charles' law. And this is V1 over T1 is equal to V2 over T2, which is equal to constant. And if we were to draw this on a graph, and this is also when pressure is constant, so if we have V volume over temperature, and when pressure is constant, we get a straight line like this, and pressure is constant. Cool, and let's go to the last gas law, which is Guy-Lussac's law. And this is when P over T is constant. So P1 over T1 is equal to P2 over T2, which is equal to a constant. And this is when volume is constant. And we've got, if we draw a graph again, P over T, P and T, we would get a straight line as well. And yeah, that's all the gas laws. And then if you were to join them together, you'll get PV over T, so 1 is equal to P2V2 over T2, which is equal to a constant. This is combining all of them. So combining. Now let's go on to Avogadro's constant and the number of particles. So let's convert number of particles is equal to the number of moles times Avogadro's constant. It's a good formula to know. And let's go on to the ideal gas equation. And this is PV is equal to nRT, where P is the pressure, V is the volume, N is the number of moles, R is a constant, and T is the temperature. R will be given in the formula sheet in the exam. And now we have an equation for Boltzmann constant, which is R, the same R from here, over NA. And yeah, so K is the Boltzmann constant. And we can use these two equations. So N is equal to NNA, and K is equal to R over NA. And if we equate NAs, so we got N over N, which is equal to NA, and NA is equal to R over K. And then if we equate these, we get R over N, N over N, which is equal to R over K. And we'll rearrange to get NK is equal to NR. And now if we look at the equation from before, this one, we can substitute the NR in that equation. So we get PV is equal to, let me zoom in. Let's zoom in. So we'll get PV is equal to NR. Instead of NR, we can write NK, large N, which is number of particles instead of number of moles. And then we'll keep T the same. So we'll get PV is equal to NKT. And this is another equation of way of writing the equation of ideal gas law. Now let's go on to work done. So say we have pressure against volume, and you go from 2 points of volume, so volume 1, V1, and V2. And the area under this graph is equal to the work done. So this is work done, which is equal to, if we look at the diagram, we have a change in V and we have a pressure P. So work done is equal to pressure times change in V, so delta V. This is work done if you have a constant pressure and a change in volume. Now, let's derive the equation for the pressure of an ideal gas. And let's go in steps. So the first step would be to imagine a box like this. Like this. Let's join it all up. Like that. And say we have a particle in this box, and it has a velocity this way, and it hits this wall, this one over here, which has an area A, and the dimensions of this box are L, L, L. We'll just, so yeah, we have a L, L, L box, and we just imagine this. Let's go on to step 2. So now, let's try find the change in momentum of a ball when it hits the wall, or the particle when it hits the wall. So we'll have the initial momentum, with mv initial is equal to mu, which u can be the velocity of the particle, and the final momentum, mv final, can be minus mu, assuming it's an elastic collision. So what is the change of momentum or the impulse? We can say final momentum minus mu minus the initial momentum, which is mu, which is equal to minus 2 mu. Cool. Now let's go on to the third step. So now we know the change of momentum. Let's try find the time between collisions. So let's look at the diagram again. So for one collision, for each collision to hit the wall again, between each collision, the ball has to travel from here all the way here and then all the way back. And this distance is 2L, so 2L. So now we know the distance is equal to 2L, and we know that the speed is u, so velocity is u. And if we use v equals d over t to find the time, we can just rearrange to do d over v. And because distance is 2L and v is u, the time will be equal to this. That's perfect. Okay, now let's go on to the fourth step. So now that we have the time and the change in momentum, we can find the rate of change of momentum. And because we have minus 2 mu as the rate of change in momentum, and then we have the time, which is 2L over u. We can rearrange and divide by the 2, so we'll get minus mu over L over u. This u can come up here, so we can get minus mu over L. Okay, now let's go on to the fifth step. Once we have that, we will need to find the force. The rate of change of momentum is equal to the force. And let's include all particles. So the force of all particles is equal to, let's make this a quantity, or like a magnitude. So we'll get rid of this minus sign over here that we have. So we would do mu, oh wait, we forgot to put the squared here because this becomes here, yeah, it becomes squared. Yeah, perfect. So we have mu squared 1 over L, and because m and L still stay the same, the only thing that changes is the speeds of each particle. So we can carry on for all the particles over L plus ... And this is equal to the force of all particles. We can just rewrite this equation as force is equal to ml, take out the ml, and then we'll have u1 squared plus u2 squared plus u3 squared, and just carry on inside the brackets. Let's move on to step 6. And now we can use a formula for the mean square speed. So the mean square speed would just be the sum of square speeds, 2 squared plus 3 squared plus ... just carry on going, all over the number of particles, which is, we can just write as u squared bar, which is the mean square speed. Now let's substitute that into the force equation that we found, this equation here that we found before. And we can just write F is equal to M over L U squared bar. And, oh wait, and times N, because then we rearrange, because if we had this thing here, so we have to move the N over here to get a value for this in terms of this and this. So now we have a nicer equation here. If that makes sense. Now step 7. Wait, this was step 7. Step 8. Let's find the pressure using the pressure is equal to force over area. So now, so pressure must be equal to M over L U bar squared N all over area, which if we look at the box again, the area is just L times L, because we have L here and L here, because this is L and this is L, so this must be L as well, because it's a box and a cube box. And so we can just write M U bar squared N over L times L squared, which is just L cubed. So we can just write this as L cubed, which is equal to mu squared N over the volume, because L times L times L is the volume of the box. So now we have an expression for the pressure. This is very convenient to have. Let's expand this to all 3 dimensions in step 9. So in all 3 dimensions, we'll just have c squared, which is the 3D speed, is equal to ux squared plus uy squared plus uz squared. And if we assume that ux squared bar is equal to, so the average ux squared is equal to the average uy squared, which is equal to the average uz squared, because of the random motion of the particles, they should all cancel out and should have all equal speeds in every direction on average, right? Because they should all cancel out in 3 dimensions because they're all random motion. So we can assume that the average speed is equal of each particle. So we can just say c squared is equal to 3, or we can just say u squared plus u squared plus u squared bar, because we can just say this is u squared bar, because for any direction, which is equal to 3 u squared bar. So now we have a good equation, and we can have substitute for, so c squared over 3 is equal to u bar squared. Now step 10, we rearrange into the original formula. So let's go to step 10. We had the formula for the pressure. So P is equal to NMU bar squared over L, volume, sorry. If we substitute the C for the 3D speed, so we'll get C squared bar over 3 over V. We can rearrange to get PV is equal to NM C bar squared over 3, which we can take out and put at the front. So let me rewrite this clearly. 1 over 3 NM C bar squared. And let me get rid of this one because this looks ugly. And this is the final formula, and we've derived it. Now, because we can just this speed here, we can just say that this is the same as the root mean square speed squared, because it's root, you have the roots squared. So we can just substitute into the original equation. PV is equal to 1 over 3 NM CRMS squared. And this is the final equation. And that's it. That's the derivation. Now let's look at the assumptions that we made for an ideal gas equation. So assumptions. we have the collisions are elastic. Collisions elastic. We have that is random motion of particles. We have that all the particles follow Newton's laws. Newton's laws. And that they move in straight lines. The particles move in straight lines. And that the time between each collision, so the time to travel to L, remember, between each collision, this collision here and then back, is much greater than the time of the collisions themselves. So when a ball or like the particle contacts and just slightly releases, so the time for this to happen is much less than the time between the collisions. So those are the assumptions. And using the formula we made before, we can actually make a lot more formulas relating to the average kinetic energy of particles. So if we use PV equals nRT, and if we have PV is equal to a third Nm CRMS squared, if we combine both these formulas by equating the PVs, so a third NMCRMS squared, if we times by 3/2 on both sides, we'll get 3/2 nRT, and then we'll have a half here, NMCRMS squared. So if we divide by n on both sides, the large M, we're going to get 3nRT/2n is equal to a half, no more n here, mCRMS squared, which is equal to the average kinetic energy of particles. So we have a nice formula here. We can also do this with the other form of the equation we had. So PV is equal to nKT, and then we have PV is equal to a third NMCRMS squared. If we equate these, nKT is equal to third NMCRMS squared. We can remove both n's, divide by n, large N on both sides, and divide by n, and also times by 3/2 on both sides, and we will get 3/2 KT is equal to a half mCRMS squared, which is equal to EK. That's a good formula that we have. It's another formula that we can get. Then, if we have n, using this equation, K is equal to R/NA, for the Boltzmann constant equation that we found before, that we just said before. If we substitute this into PV is equal to nRT, or nKT, sorry, so nKT, we'll get PV is equal to n R/NA T, and if we use the other equation, PV is equal to a third NMCRMS squared, and we equate, we'll get n R/NA T is equal to a third NMC squared RMS, CRMS squared, sorry, from here and here. And we can rearrange the equation to get similar to before. Take away n's on both sides, RT/NA, and then times 3/2, and we'll get a half mcrms, just like before, which is equal to average kinetic energy. And here we have another equation. And here we have three equations that we just found using the derivation and the ideal gas equations in their different forms. Now let's finish on Brownian motion. So let's go to Brownian motion. Brownian motion. So Brownian motion came from pollen particles in water that looked like they had very random movements. So very random movements. They moved around like this. And to explain this, what Robert Brown said was, if you zoom in to what's happening in here, we can see that the pollen particles, if you make a big pollen particle like this, and what there is that there's small water molecule particles which push on different sides different amounts. So say if there's more on this side, there'll be more of a force here, and because there's going to be different amounts of forces at different sides, it's just going to cause a really random motion at different points. So because there's a slight imbalance, because when you get larger, you don't see the Brownian motion because these forces cancel out. So that's why you don't see like people moving around in random directions because of the wind. But yeah, this explains Brownian motion, because there's small particles like these, the water molecules small, acting on a big pollen particle, and there's small differences in pressure or collisions in each side. So there's more collisions on this side and there's less collisions on this side, cause the force to go this way, and at other points it will cause it to go different directions. So you'll get, if you get the motion start off like this, you get from start off like this, then you'll have a different motion over here and then a different one over here. So you'll get something like this, and you'll get random motion later on. And that's a recap of all thermal physics. I hope you enjoyed. Thanks for watching.